for introducing me, and I'm also thankful to the organizers for giving me this nice opportunity to talk. Let me start my talk titled Ricci Solitions in Almost Contact Geometry. I read my manuscripts. A Riemannian manifold, MG, G is a Riemannian metric, is a Ricci solution if there is a smooth vector field W on M satisfying this equation. We call Ricci solution equation, this equation, for some constant lambda. A Ricci solution with W0 or killing is reduced to Einstein equation. We easily see this fact. And it is said to be shrinking, steady, and expanding according as lambda positive, 0, and negative respectively. If the vector field W is gradient of some function we call potential function minus phi, here the minus sign is just a conventional region, not essential part, then G is called the gradient Ricci solution, and equation 1 assumes this form. His Hessian F is Ricci minus lambda G. In the study of string theory, theoretical physicists also have been looking into this equation of Ricci solutions. Indeed, in Priden's paper, the author also refers to G as a quasi-Einstein metric. Hamilton and Ivy proved that a Ricci solution on a compact manifold has constant covers in dimension 2 and 3 respectively. Here is the famous papers, Hamilton's paper and Ivy's paper and Priden's paper. Ricci solutions, main Ricci solutions have two phases. One is a natural generalization of Einstein manifolds, and at the same time is self-similar solutions to the Ricci flow equation with initial metric G0 is G. Here the Ricci flow equation, round T, GT is minus 2 times Ricci GT. For details, we refer to Hamilton's paper in 1982, TGA, JDG, and Chow and Knapp's text. Today, in my talk, all manifolds are assumed to be connected, orientable, and smooth. Almost contact manifolds are phrased as 2n plus 1 dimensional manifolds whose structural group is reducible to un times 1. This is equivalent to existence of an endomorphism field phi, a vector field psi, and one form eta satisfying these two equations. We call psi the Rip vector field. Here we remark that a compact orientable manifold of odd dimension has the Euler characteristic 0, and then it has a non-vanishing vector field. Anyway, then one can always find the compatible metric, Riemannian metric, satisfying this relation for all vector fields and xy. Such M phi psi eta G is said to be an almost contact Riemannian manifold or an almost contact metric manifold. Here the fundamental two form phi, capital Phi, is defined by this, and in addition M satisfies d eta is phi, then M is called the contact Riemannian manifold. Here we may raise the following two fundamental questions. The one is find Ricci solutions in the framework of almost contact geometry. And the second one, could we establish a compatible flow to almost contact structures? I reviewed briefly the almost contact geometry. In case that their automorphism groups have the maximum dimension n plus 1 square, they are classified by the following three classes. Is proved by Danno in 1969. One is Sasakian space form, that is complete simply connected normal contact Riemannian manifolds of constant holomorphic sectional curvature. And the second one is R times the real line times the product space of real line and the complex space form of holomorphic sectional curvature K, or the circle, the product of circle and the complex space form. The third one is a warped product space of real line and complex Euclidean space by a warping function rho. Here is rho is the exponential function of R by positive constant factors. Each these three classes has been extensively developed. For the class 1, the contact metric structure, including Sasakian structure, has been investigated by many authors. We may refer to Blair's text. And the geometric property of 2 is represented as the so-called cos-symplectic structure. The trivial products of a real line or a circle and the Kähler manifold admit such a structure. Extending the model 3, Kempmuth introduced another class which is expressed locally by a warped product space of an open interval and the Kähler manifold. We call such a manifold a Kempmuth manifold, and corresponding structure is called the Kempmuth structure. Here, omit. A Sasakian cos-symplectic or a Kempmuth manifold holds the CR integrability and more of the normality. Here the Blair's text and the Kempmuth paper. I'd like to omit this part, associate CR structure and normality. Without normality condition, we have much broader classes. An almost contact metric manifold is said to be almost cos-symplectic if T equals 0 and T phi equals 0. Such a class was introduced by Goldbeck and Yano, and the trivial products of almost Kähler manifolds and the real line or a circle are the simplest example of such manifolds. Recently, Perrone classified all homogeneous almost cos-symplectic 3 manifolds. Another one, an almost contact manifold is said to be almost Kempmuth if T is 0 and T phi is 2 times eta wedge phi. The warped products of an almost Kähler manifolds and the real line gives example of almost Kempmuth manifolds. And further properties and examples of such manifolds we refer to Dilleo and Bastor's paper. Here's a Goldbach, Yano paper and Perrone and Dilleo, Bastor's paper. Now we first may consider Ricci-Soliton, whose potential vector field is Riemann vector field. The previous talks, many people studied the Riemann vector field. 1 over 2 L psi g. Here L is the differentiation with respect to Riemann vector field psi g plus Ricci tensor minus lambda g is equal. Then we prove the theorem 1, a contact Ricci-Soliton. Contact Ricci-Soliton means contact metric manifold satisfying this equation. Then is Sasaki Einstein. In particular, in dimension 3, we have a 3-dimensional contact Ricci soliton is Sasakian and of constant curvature 1. This result is published in this paper in 2011. Now we look at almost consplecting manifold. We prepare some fundamental formulas which are mainly established in Olstach's paper. Then you have fundamental formulas. Psi is already a geodesic vector field, and phi is parallel with respect to the real vector field. And the number x psi is minus phi h x. Here h is 1 over 2 x psi phi. Then we find that the linear operator H is self-adjoint, and moreover, it satisfies these equations. From 4 and 5, we obtain that divergence of psi is 0. Moreover, from 4, we have the characteristic or the structure Jacobi operator written by this formula. From 6, we also obtain the Ricci curvature for the direction, direction plus trace over h square is 0. So Olstach's paper, and Kim and Hong-Kyung Park and Kim's result on almost consplecting manifold is normal if and only if the canonical foliation phi, which is generated by the contact distribution D, is tangentially scalar and H vanishes. Now we prepare the following lemma. Is a general for a general Ricci soliton over Riemannian manifold. Then we have 1 over 2. The square of the norm of LVG is DRV plus 2 times divergence lambda v minus SV. Here R is the scalar curvature of M, and S is the Ricci operator associated with Ricci 2 tensor. Now we suppose that almost consplecting manifolds admits the Ricci soliton G for the direction for the potential vector field psi. Then from 1 we get easily this formula, and use 4 concerning this part, now x psi, to obtain this or this, putting x equals psi. Then since h psi is 0, we have the psi is the eigenvector of Ricci operator. Since the trace of phi h vanishes, we find also that the scalar curvature is constant. Now we assume that in our lemma, we putting psi, then you have already psi becomes a killing vector field. Then equation 10 is that again M is Einstein. From 7, this part vanishes, so and then the soliton side is 0 and the Ricci soliton is steady. Thus we have theorem 3, an almost consplecting manifold admits a Ricci soliton if and only if psi is killing and M is Ricci flat. Together with proposition 1, we have the following corollary. And the almost consplecting manifold whose canonical foliation is tangentially scalar if it admits a Ricci soliton G psi, then M is a consplectic and Ricci flat. In dimension 3, a three-dimensional almost consplecting manifold admitting a Ricci soliton G psi is consplecting and locally flat. Corollary 3, a conformally flat almost consplecting manifold admitting a Ricci soliton G psi is locally flat. Next, we studied gradient Ricci solitons. Unifying almost complex structure and almost scalar structure, a notion of an almost alpha complex structure is defined by the following equations. Theta is 0 and d phi is equals to 2 alpha times eta wedge phi. Actually, when alpha is 0, these two equations give an almost complex structure, and when alpha is 1, these two equations give almost Kenmoch structure. So this equation unifying those two structures. Let M be an 2n plus 1 dimensional almost alpha Kenmoch manifold. We prepare some fundamental formulas like in the complex case. We have these equations, and similar to complex case, an almost alpha complex manifold is normal if and only if the canonical formulation is tangentially scalar and h is 0. And now let be an alpha complex manifold, then such manifold is locally characterized by the following two conditions. We may consider this manifold is counterpart of Sasakian manifold. From the second one of 14, we have this curvature condition, and Ricci, we have Ricci curvature. Like Ricci xi is minus 2n alpha square times eta x. In dimension 3, Gauche showed that Kenmoch metric is a Ricci soliton, then it is of constant curvature 1. Now we extend his result without dimension restriction in the context of almost alpha complex structures and gradient Ricci solitons. Theorem 4. Let M be an almost alpha complex manifold with H0. If G is a gradient Ricci soliton, then M is almost complex, that is alpha is 0 or Einstein. Look at briefly the proof of because I was so enough time. The equation 2 is the gradient Ricci soliton equation, can be written as this. We developed this equation, then we have this. We one more differential covariant this, and we have this. And we put y is xi, then we have this. And this may be almost complex condition. Then to get this, from which we find the right hand side of this side vanishes. And from 15 we compute this part. Hence, equation 18 is that either equation 18, this equation is that either alpha is 0 or this. Then from this relation we have this gradient f proportional to psi. This equation turns out to be also this. Its exterior derivative implies this. Since theta is 0, we can see that psi f is constant. This vanishes, so psi f is constant. We put psi f equals beta. Then from 17 and 19, the Ricci two tensor is written simply, like this one. Here, since psi is a eigenvector of Ricci operator, the constant factor is minus 2n alpha square. We immediately there lambda equals minus 2n alpha psi. So the Ricci-Soliton behavior is steady or expanding for alpha 0 or negative. For alpha 0, then the soliton is steady or not, then it's expanding. And then 20 gives this. We remember that famous identity x. Here tau is scalar curvature, is better than is scalar curvature is 2 times this when local frame field EI. And use this identity, then we get this relation, which gives us beta is 0. When beta is 0, we easily state here beta, f is constant and m is Einstein. Moreover, this is expanding. This completes the proof. Then we have corollary 4. A alpha cosplexing manifold is with a gradient Ricci-Soliton is cosplexing or Einstein. Actually, we have an example for a Keller-Einstein manifold N and the real line R. A cosplexing manifold N cross R is a gradient Ricci-Soliton. Explicitly, the potential function is lambda t square over 2, where t is, belongs to R. Such a gradient Ricci-Soliton is said to be rigid. Is investigated by Patterson-Wiley in 29. Remark: a alpha Kenmode manifold, here alpha is non-zero. Manifold does not admit the Ricci-Soliton is the potential vector. V is the Lie vector field. We omit the detailed proof. Now we finally look at real hypersurface in Keller manifolds. Let M be an orientable real hypersurface of Keller manifold, M tilde, J, G tilde. Here, G tilde is a Keller metric, and J is almost complex structure, and large N be a global uninormal vector field on M. Then we have these fundamental relations. Jx is the tangential part and normal part. Then defines tensor phi and eta, and Jn is minus psi defines the Lie vector field psi. Then moreover, we find that phi psi eta g is an almost contact metric structure. This study is well developed by many many peoples. A real hypersurface of a Keller manifold is said to be a Hopf hypersurface if its structure vector is principal curvature vector. Then we first find this theorem. If a compact real hypersurface M in a Keller manifold admits a Ricci-Soliton whose potential vector field is Lie vector field, then psi is already a Killing vector field and M is an Einstein manifold. The compact condition is necessary. More similar to the proof is the previous, almost cosplexed case. Here developed Ricci-Soliton equation for the vector field psi. Then we have this. From 10 we have the fundamental equation for real hypersurface in Keller manifold. Then we have this part turns to be this. And taking the trace of 23, then this part vanishes and scalar curvature is constant. Then by fundamental lemma 1, we have size killing vector field and emission Einstein manifold. In the proof of theorem 5, you easily find that if a Hopf hypersurface compact condition is replaced by a Hopf condition, if a Hopf hypersurface M in a Kähler manifold admits a Ricci-Thornton whose potential vector field is Ricci vector field, then Xi is killing and M is already the Einstein manifold. Moreover, we have the following results. If a compact real hypersurface in complex Euclidean space is a Ricci-Thornton whose potential vector field is Ricci vector field, then is a sphere. This is my collaborator Makoto Kimura in Ibaraki University. Cho and Kimura proved if a compact and contact type means that phi a plus a pi is k phi, k is positive constant. Satisfying that relation we call a real hypersurface is a contact type. Then in a complex number space is a Ricci-Thornton, then M is a sphere. There do not exist real hypersurface complex projective or complex hyperbolic space. Usually we call the non-complex space form, we call, which are Ricci-Thorntons with the Ricci vector field as a potential vector field. There do not exist. So we proved that there do not exist compact Ricci-Thorntons among Hopf hypersurface in complex projective of hyperbolic space. Another one, there do not exist ruled real hypersurface in a non-flat complex space form, which are gradient Ricci-Thornton. Ruled real hypersurface is a totally geodesic foliated real hypersurface, roughly speaking. This is my two papers. Recently, in private communication with Professor So, we find that there do not exist Hopf hypersurfaces complex two-plane Grassmannians G2CM plus 2M greater or equal to 3, which are Ricci-Thorntons with Ricci vector field as a potential vector field. They do not exist. Finally, this morning's talk, Hashinaga and Tamaru, here is another their result. A Lie hypersurface is an orbit of a cohomogeneous one action without singular orbits. Very recently, Hashinaga, Kubo, and Tamaru obtained an interesting result in terms of algebraic Ricci-Thornton. They explained well this notion. Then they proved that a Lie hypersurface in a complex hyperbolic space is a Ricci-Thornton if and only if it is whole sphere or n is 2 and it is the homogeneous ruled minimal hypersurface. Next part is something interesting part, but I have no time, so I'd like to hold this part till next time. Thank you for your attention.